Okay. I think we could start. Welcome, welcome. Happy Tuesday after your second test. I believe, I'm not mistaken, I hope I didn't miss anything, that I have finished grading, or applying, the partial credit for test 2. So let me know, if you have any specific questions about your test. Happy to talk with you about them after class. If you have general test questions, that will apply to everyone, that's great. I could talk about them now, but specific questions, related to your test, I think it'd be good to talk individually. Any questions about that? Okay. Great. Well, we are going to start test 3 today, or excuse me, test 3 material. We're not going to do test 3 today. You've probably seen this, but a couple things on here that I wanted to point out. If you look at the up to test 3 module, which we will begin today, click on that. Everything is posted here. I'm going to give you fair warning that these handouts from like 17 to the end, these may need updating. The ones above that are fine, 14, 15, 16, but these, I'll try to warn you if I update them. I have been going through those and have noticed several, the material got changed a year ago, it got rearranged, and it doesn't look like the PowerPoints themselves were rearranged. So I'm having to do some back work for that. So if you've already printed all those, I am sorry. I printed them as well and then realized, oh, these are not correct. So try to maybe print them 3 at a time instead of everything at the same time. This is our last unit test for our class. So this will take us all the way up through May 6th. The class period after that, the Thursday, we'll review for the final exam, and then our final exam will be from 3 to 5 p.m. on Tuesday, May 15th, or 13th, excuse me. Questions on that? So we're looking at the end of the semester. We're in our last third. Okay. Let's go ahead and jump into today's material then. Let's start this module. Oop, that is not what I want. We do not want to solve complex equations again. We want to do graphs of lines. Interesting. That was called the wrong thing, that's why. Okay, well, I apologize. Give me a moment to go pull that PowerPoint. Because apparently I did not do that. One day, we'll get there. Just not wanting to take me there very quickly. All right. I think it's here. I have every other file saved, but not that one. I think. There we go. Okay, we're back. Let's start this now. So the last test talked a lot about some basic algebra skills. So we did a lot of equation solving, we did stuff with percents, stuff with formulas. We are going to move to graphs. This throughout most of the test 3 material. Graphs are things related to graphs. So this week, we are going to introduce graphs of lines. Next week, we're going to kind of expound on that. I'll give you a little heads up that this is lesson 14. We'll do lesson 15 Thursday, lesson 16. So Tuesday next week, there will not be a quiz. There will instead be a project. Lesson 16, I'll go ahead and make that note. Lesson 16. You will get a project instead of a traditional quiz. And you'll see why that is as we kind of go through lesson 16. It's hard to do a Canvas quiz for the material from lesson 16. I'll give you more on that when it gets closer, kind of explain how the project will work, but I wanted to at least let you know about that. Okay. So let's talk about graphs of lines. First, this requires that we know a little bit about the coordinate plane. The coordinate plane is essentially the tool that we use to picture relationships between variables. So we have dealt with formulas and equations that have various variables in them. We want to be able to create a graph or a picture of that relationship, not just show it algebraically. And the coordinate plane is what we use to do that. I'm going to kind of assume that you have seen this before, so not go through it in great detail. The coordinate plane, it is divided into 4 quadrants by axes. So I have this x-axis, the horizontal axis. I have this y-axis, the vertical axis. And it divides the plane into 4 parts, which we call quadrants. Quadrants, 4 parts. The top right quadrant, we call quadrant 1. And then as you move counterclockwise from there, the quadrants go up. So 1, 2, 3, and 4. Both the X and the Y axis are number lines, so they have increments on them. So if you follow the number line, that tells you, okay, how far am I moving right? How far am I moving left? How far am I moving up? How far am I moving down? Okay. Every location on this coordinate plane, we can give an X value and a Y value. For example, this point here, where the 2 axes intersect, we call the origin. And it has X coordinate 0, Y coordinate 0. That would be the coordinates or the ordered pair that we could call that particular location the origin. And let's talk a little bit more about ordered pairs. As mentioned, points on the coordinate plane are described using these ordered pairs. So these pairs that have an X and a Y part. So ordered meaning X, then Y. So X standing for that vertical axis movement in the vertical direction. Y standing for how far you move up or down on that horizontal axis. If we combine the X and the Y parts together, we have a particular location. And we call that an ordered pair. We surround it with parentheses and put a comma between. These 2 numbers, X and Y, are called the coordinates of the points. First number represents the X coordinate. Second represents the Y coordinate. And using these coordinates, we're able to locate different places on the coordinate plane. For example, let's see, this is kind of far away. Let me zoom in a little bit. Let's consider this location of point A. Okay, A has coordinates 5, 3. So 5 is my X coordinate, 3 is my Y coordinate. To get to the location 5, 3, I'm going to start at the origin, and I'm going to move in the X direction 5. So X tells me how far I move left or right. It is positive, therefore I'm going to move right 1, 2, 3, 4, 5. And then Y tells me in which direction I move up or down. It is telling me a positive 3, therefore I'm going to move 3 up, 1, 2, 3, to get to that location where the point A exists. So if you ever want to find the location of an ordered pair, you're going to start at the origin, and you're going to move first coordinate left or right, second coordinate up or down. I'm not going to go through all of these, but I think it is worth doing a few more. Let's do B. So B has coordinates 0, 4. It's right here. And again, first coordinate is X, second coordinate is Y. First coordinate tells me to get to that location, how far do I move up or down, or excuse me, left or right. Second coordinate tells me how far do I move up or down. Since the first coordinate is 0, then I'm again going to start at the origin, and I'm not going to move left or right at all, since I'm told to move in the X direction 0. Y is 4, therefore from that location, I'm going to move up 4. 1, 2, 3, 4, to the location of B. So B is located where it is shown on the coordinate plane. Couple more. let's do D, or excuse me, let's do C. C, where is C? 3, 0. It has coordinates 3, 0. Let's find it on the coordinate plane. It is right here. Okay. And again, it's X first, then Y. So we're told to move 3 in the positive X direction. So 3 to the right, starting at the origin. I'm going to move 1, 2, 3 to the right. And then the 0 tells me I'm not going to move up or down at all. So the point 3, 0 is right there on the X axis. Let's do one more. Let's do D. Our coordinates can also be negative. Could be negative or positive. But they mean the same thing in terms of directionality. If I want to find the location of point D, it's already shown on the coordinate plane, but let's go ahead and show how we got there. D is right here. Okay. We are told, starting from the origin, to move -6 in the X direction. That negative tells me instead of going right in the positive X direction, I'm going to go left from the origin. I'm going to go 1, 2, 3, 4, 5, 6. And then the positive Y tells me from that point, I'm going to go up 6. 1, 2, 3, 4, 5, 6. And I land on that location, -6, 6. So Y were to have been negative, I would have gone down instead of up. Questions on any of those? Okay. So we can state any location by an ordered pair, by a pairing of an X part and a Y part, given this type of coordinate plane, which is the most common type to use. Maybe you've played Battleship, similar to that. Above, these were just kind of a scattering of locations. Typically our goal when we are given ordered pairs is we want to be able to show some sort of relationship between variables. So we've got two variables here that we are comparing, as mentioned, two axes, allowing us to compare relationships between the variables X and Y. If I am given a set of ordered pairs and I plot them on the coordinate plane, what we're normally going to do is we're going to look for some pattern in the locations, such as a set of points lining up in a straight line. Let's see how that works below. And this is a little bit different. Above, we were given ordered pairs. It's really common for ordered pairs to be given in a table with X coordinates and Y coordinates. So for example, this top row, -2, 5, would represent the ordered pair -2, 5. Next row would represent the ordered pair -1, 3, etc. So it means the same thing, it's just organized slightly differently. And we know that ordered pairs mean locations on the coordinate plane. On our table, these kind of look just like a bunch of numbers, but if we were to graph these, it would show us that there's a pattern in the relationship between the two variables. So let's go ahead and put these on the coordinate plane. Maybe I'll do them in colors. This first one in red, blue, green, yellow, black. Okay. So -2, 5, we're going to start at the origin and we're going to go to the left 1, 2 and up 1, 2, 3, 4, 5. That's the location of that first coordinate. -1, 3, I'm going to go to the left 1 and up 3. 0, 1, I'm not going to go left or right at all. I'll start at the origin and just go up 1. Told by my Y value. 1, -1, second to last ordered pair, I'm going to go to the right one. And then instead of going up one, I'm going to go down one. And then finally, 2, -3, I'm going to go to the right 2 and down 3. There we go. Extra little point in there. All right. And these points appear that they are all on a straight line. And that line is going down from left to right. One thing that we are going to very quickly get to is if I want to graph an equation rather than just a set of ordered pairs, our process will be to find a few ordered pairs that will solve the equation. And then once I have established a pattern, I can connect the dots. Create a line showing that pattern or that relationship between the variables. Okay. All right. Well, let's do that. Let's bring in some equations. If I am given, say, this equation on the right, we have in the previous module, we've been asked to solve certain equations for variables. This module will be given equations with 2 variables specifically. And instead of wanting to find one single solution for one single value of a variable, we are wanting to create a picture of all possible solutions to show the relationships between variables. This is kind of a principle of mathematics that if you have one equation and 2 variables and there are an infinite number of things of ordered pairs, that will solve that equation. If we want to show that relationship, then we can create a table of values. So I'm going to lean towards tables rather than ordered pairs just because I think they're better organized. I'm going to start by, I'm just going to pick 3 values for x, write them under the x column. Here our 3 values are picked for us, but generally you can pick any x value that you want and put it in this column. I like to pick a variety, like some negatives, 0 is good. A lot of times I'll choose a positive as well. Variety gives me a better idea of what the graph might look like. I can now use the equation to find values for y that when paired with that value for x makes the equation true. For example, if x is equal to -3, that first value for x that we chose, then I can take this equation and substitute -3 for x, stuff 4 in there. And then on the right-hand side, -3 plus 4 is 1. So it looks like if x is -3, then the corresponding value for y that should be in that table is that y is 1. And I can do exactly the same thing with the other values for x. If x is -1, then we could say that y is equal to, instead of plugging in -3 for x, I'm going to plug in 1. -1 plus 4 is 3. So if x is -1, it looks like y is 3. Similarly, if x is 0, then we can use that exact same equation, replace x with 0 instead of with -1. And then I can simplify the right-hand side. 0 plus 4 is 4. So we have written each row as an ordered pair, the pairing of x and y values. Once we have this done, once we have a good collection of pairings of x and y using that equation, I can take these values and I can put them on the coordinate plane. let's do that first. And then we'll talk about this a little bit. Okay, I just recreated the table below. I will map like this. Okay, so the point -3, 1. 1, 2, 3 to the left, 1 up. There. The point -1, 3. -1 to the left, and then 1, 2, 3 up. There. And then the point 0, 4. 0 to the left or right, and then 1, 2, 3, 4 up. Those all do look like they are on a straight line. We would not have been able to tell this relationship with just one ordered pair. So if we would have said, okay, this is a solution if x is -3 and y is 1, all I would have had would have been this. And there's no way that I could tell any more than that one single pairing of values. I couldn't see any pattern between the two. But since we chose 3 different values for x, that'll allow us to see a pattern here. Once I have that pattern established, I can connect the dots with a straight line, or as straight as I can get it with this clunky little ruler. Okay, there we go. Okay. Any questions on that so far? All right, and I'm hoping this is somewhat familiar to you. Maybe it's just been a bit since you've seen it. Let's see, how many more examples do I have? Several, excellent. Let's do some more examples. Let's say we're given this equation. Maybe I'll give myself some more room up here. I'm given the equation -6x plus 2y is equal to 6. And we want to find several ordered pairs that are solutions to this equation, plot those ordered pairs on the coordinate plane, and then once we see a pattern, connect the dots with this particular section. They're all going to be straight lines. Okay. Let's see, looks like we don't have to choose our own x values here. We are given the x values. Sometimes you will have to choose your x values, but here they're given. So let's utilize that. First one says x is -2. Let's substitute that into our equation for x. -6 times a -2 plus 2y is equal to 6. Okay. This one's a little bit more tricky because y is not by itself on one side of the equation. But we know how to solve equations now, so let's go ahead and do that. Looks like I have parentheses first, so let's multiply. -6 times 2 is 12, plus 2y is equal to 6. Okay, this is a simple equation now. I can deal with the addition, subtraction, by subtracting 12 from both sides. I get 2y is equal to 6 minus 12 is a -6. And then finally, I can deal with that multiplication. Divide both sides by 2, and I get that y is equal to -3. So it turns out that if x is -2, y is equal to -3, giving me that ordered pair, -2, -3. That tells me a location. Okay. That tells me one ordered pair. We just said that if we want a good picture of the relationship between these variables, we need at least 3 ordered pairs. We are given more values for x, so we could find more than 3 ordered pairs. I probably will just do 3. If we wanted to find another ordered pair, I'd have to do that same process again. I would have to plug in -1 for x. I would have to multiply and then subtract whatever I get when I multiply. I would have to then divide, and that would finally give me my value for y, which is a little bit more work. It's not a terrible situation, but it's some work if you have to do several of these. So to make things a little bit easier, I'm going to start by, instead of plugging in a value for x, let's solve the equation that we are given for y. So I have this equation. The equation is -6, or excuse me, need my y, or yes, -6x plus 2y is equal to 6. The previous equation that we had up here, it had y by itself on one side. So plugging in a value for x, it made it really easy to find the y value because the equation was already solved for y. This equation below, unfortunately, does not have that feature. But I can rearrange it so that it looks like that. Let's solve this equation for y, which means get y by itself on one side of the equation. Okay. So it looks like on the left, we started solving for y on the left when there's a number there for x by multiplying and then subtracting whatever I got when I did that multiplication. Okay. Or doing the opposite operation there. I can do essentially the same thing here. I can't really multiply x by -6 because I don't know what x is, but I can move to, okay, let's take this x term and let's move it to the other side of the equation. Let's get it off that side that has y. And I'm going to do that by performing the opposite operation, just like if these were numbers. So let's see, -6x. If I want to perform the opposite operation, I'm going to add 6x to the side because -6x plus 6x is 0. I'm allowed to do that as long as I do exactly the same thing to the other side. Okay, so that means these two sum to 0. These two go away. What I'm left with on the left-hand side is 2y. That is equal to 6 plus 6x. These two are not like terms. Not like terms. One of them has a variable, one does not. Therefore, I can't combine them. I just have to write them as they are with a plus sign in between them on the right-hand side. Okay? So don't put them together as 6x 6. Or 6x times 6 or something like that. It's addition connecting those two, it's not multiplication. So now that looks a little bit better. I at least have the y term by itself on one side. It looks like here, when we solve this equation, to get y by itself, we divide it by 2. We can do the same thing here. The only thing that we have to do a little bit differently when I have two terms that are added together on the right-hand side is just like multiplication distributes over a sum, so does division. I have to distribute the division and divide both terms by 2. Because they're being added together. So that leaves me with, let's see, these will cancel. That leaves me with y on the left is equal to 6 divided by 2 is 3. Now I still have the x plus 6 divided by 2 is 3. So this equation, it means the same thing, has the same relationship between the two variables as this original equation does, but if I want to choose values for x and find the corresponding values for y, This one will be a lot easier to work with. We won't have to rearrange the equation every time. We can just simplify the right-hand side. I can now use this equation to solve for y, or excuse me, to find y values. And we're going to do this several times. So hopefully you will get used to this. Same thing we were doing before, except we just have more than one variable. So let's see, we already found what y is when x is -2. If x is -1, let's go ahead and use this new form of the equation. I can say y is equal to 3 times the -1 plus 3. And now the right-hand side is easier to work with. 3 plus the -1 is -3 plus 3. -3 plus 3 is 0. So I had 2 lines of work instead of 4. If x is 0, then y is equal to 3 times 0 plus 3, which is equal to 3 times 0 is 0 plus 3, because I multiply before I add. 0 plus 3 is 3. Okay, and just for the sake of showing it, let's go ahead and find the other two. If x is 1, y is 3 times 1 plus 3, which is 6. And then if x is 2, I won't show all the details for this one. Y is 3 times 2 plus 3, which is 9. Okay. Questions on that one so far? Okay. Well, this, as mentioned, these slides were rearranged. So let's go ahead and take what we just did. And let's put those ordered pairs on the coordinate plane. Okay. Let's blue, red, green, yellow, black. -2, -3. I'm going to go to the left through, at the left 2, down 3. Can't talk. Ooh, that does not look like it is on the intersection. There we go. -1, 0. I'm going to go to the left 1 and not up or down at all. 0, 3. Not going to go left or right at all. Just going to go up 1. 1, 6. I'm going to go to the right 1 and up 1, 2, 3, 4, 5, 6. And finally, 2, 9. I'm going to go to the right 2 and up 6, 7, 8, 9. There we go. And it does in fact appear that all 5 of the, ooh, what happened there? Try that again. All 5 of those ordered pairs are on the same straight line. So we can draw one straight line to connect the dots. If I can get my ruler situated. There we go. Okay. Questions on that? All right. These next couple of slides, just for the sake of you having them in your slides, shows how to solve those equations for this equation for y, and then your graph is given below. That's on the blank slide as well. That's the stuff that we just did, so I won't go over it again. Let's see here. How long do we have? I think that we are actually going to do, we got more of these in a bit. No, we should go ahead and do a couple. I'm not gonna do both of these. I'm just gonna do one of them. We are going to go through some more examples of solving an equation for y later. So again, I won't do both of those, but I will do one. Let's do number 2. Number 2, no, let's do number 1. 6x plus 3y is equal to negative 24. So we're not going to, oh, I see what I did. I apologize. We're going to solve both equations for y. I know now. As mentioned, these got rearranged. So I don't 100% remember what I decided, but let's go ahead and solve both equations for y. So number 1, I have a negative 6x plus 3y is equal to negative 24. My goal is this variable I want by itself on one side. So I'm going to observe the operations that are being done to that variable. It looks like there is a negative 6x being added to that variable. So I'm going to start by undoing the addition, just like I did when I faced a simple equation. I'm going to start by going backwards with PEMDAS. Okay. We will add 6x to the left because negative 6x plus 6x gives me 0. That leaves me with 3y is equal to, again, these are not like terms. I can't combine them. So I have to just write that right-hand side as 6x minus 24. Okay. So one step down. If I want to get y by itself now, I can focus on multiplication. So I can divide that left-hand side by 3. That's all well and good. But I have to remember that because I have subtraction in between those two terms, I have to distribute that division on the right. I have to do exactly the same thing to the left and to the right. So I'm going to divide both the 6x and the 24 by 6. That leaves me with y on the left is equal to 6 divided by 6 is 1, x. 24 divided by 6 is 4. Y is equal to x minus 4 would be that first equation solved for y. Again, it shows the same relationship between the variables. The graphs will be the same regardless of which form you use to find the ordered pairs, but that latter one is a little bit easier to work with.
Okay, you lost me on that one.
Okay, which part?
So you have 3y on one side and you put.
Oh, I see. Yes, I lost myself, didn't I? That should be. That's probably why I lost you. Great. There we go. So y is equal to 2x minus 8. Is that what happened? Great. Makes sense now? All right. Wonderful. I'm glad you're catching me on this. You're right, that didn't make sense. So the second one, 2x plus 4y is equal to 8. We are again trying to isolate this y. So I'm going to start with addition subtraction. There's no parentheses to deal with here. So let's undo that addition of 2x by subtracting 2x from both sides. Because 2x minus 2x is 0. That gives me 4y on the left equal to, I like to write the x term first. You could write this right-hand side as 8 minus 2x if you want, but I like to write the x term first, and we'll see later why that is. I now have the 4y by itself. I can finish up by dividing that left-hand side by 4, and I will divide the right-hand side by exactly the same thing, as you all were letting me know. Okay. So that leaves me with y on the left is equal to, the 8 minus 4 isn't bad. or 8 divided by 4 isn't bad. 8 divided by 4 is 2. We are going to see very soon that if you have something that looks like this, where the numerator is larger than, or the numerator is smaller than the denominator, it will be more helpful to us to write this as a fraction. So -2 over 4, I want to reduce this fraction. I can divide the top by 2 and the bottom by 2. Which leaves me with what? -2 divided by 2 is a -1. 4 divided by 2 is 2. So that gives me 1/2 x, -1/2 x plus 2 for our simplified equation solved for y. Questions on that? That one better? Okay, great. Let's see here. Well, now that we have seen that fractions can be involved, let's talk about a characteristic of a linear equation. All of the equations that we've thus far graphed. So we found the ordered pairs, put them on the coordinate plane, connected the dots, and then took a little aside and talked about how to solve an equation for y. All of those equations that we've graphed have had graphs that are straight lines, as will be the case for everything in this module, or in this lesson. We can start coming up with easier ways to graph, or ways that we can kind of describe a linear equation. What are its characteristics that will help us to analyze the equation and to kind of get an idea of what the graph might look like without even plotting any ordered pairs. The slope is one such characteristic, which you have again probably heard of, but I don't know if it has been recently or sometime in the distant past. One characteristic of a line is that it is slanted. So some lines are very steeply slanted up, some lines are less so, some lines are slanted down, etc. Some lines are horizontal. The slope tells me how slanted a line is, essentially. So it tells me if I'm given a line, how bad is the slant. Mathematically, we can think of the slope as the ratio of the change in y over the change in x. So change in y would be the difference between the y values. Change in x is the difference between the x values. It's also often called the rise over the run, and graphically this makes a little bit more sense. Let's look at that on the right, see how that works. Let's say we're given these 2 points, -1, 0, and 0, 3. Then I want to think about how much would I change in the y direction, or up and down, to get from that point -1, 0, and 0, 3. Well, here I'm going to go, let's see, in the vertical direction of the y direction, 1, 2, 3. That's all I would need to move up. Therefore, the rise, or the change in y, is 3 for this particular line. So I took 1 point on the line and a second point on the line, and I figured out, okay, how far do I have to go up to get from one point to the other? If I take the ratio of that and the run, I have the slope. To find the run, I have to figure out, well, how far do I move left or right to get from one point to another? I can go from this location. I can note that if I move 1 unit to the right, I get to that x value. or that ordered pair rather. So the run in this case is 1. I can take the ratio of, in this case, the rise, which is 3, over the run, which is 1. And for this particular graph, that tells me that the slope is 3 over 1, or just 3. So if the denominator is 1, we can write it as a whole number. If the denominator is not 1, I'll generally want to write it as a fraction. Questions on that so far? Okay. Well, we can determine the slope of a line graphically if we can find 2 points on the graph of a line. We can also determine it algebraically. There is a formula that you can use to calculate slope. Very helpful formula to have. So if you have 2 points, x1, y1, and x2, y2 on a line, these can be any 2 points. Doesn't matter what the 2 points are. Any 2 points on a line. Then you can use the formula below to determine the slope. That formula is y2 minus y1 over x2 minus x1. So on top, we're going to subtract the 2 y values from the ordered pairs. So 2 y values here and here. And then on bottom, we're going to subtract the 2 x values from those ordered pairs from the points on the line. We will find their ratios, or their ratio of those 2 subtractions, and that'll tell us the slope. Let's say, I know it's worked out below, but let's go ahead and work it out. Sometimes it's easier to start from the beginning. Let's call x1, y1. Let's call that the point 0, 3. I could have called the other point, x1, y1. It doesn't matter which point you give the 1 indices. And then I'll call my second point x2, y2. Let's let that be -1, 0. I could have flip-flopped them, doesn't matter. We'll get the same result. If that's the case, then my slope, which we are in the next lesson going to start notating as m. I really have no idea who came up with the m as the letter we use for slope, but it is commonly used. Slope, or m, is equal to y2, which is 0. And then there's a subtraction sign in my equation, minus y1, which is 3, divided by x2. See if I can find another color here. X2, which is a -1. And then again, there's a subtraction sign in my equation, minus x1, which is 0. Okay. So we're just substituting everything in. Have to remember that I have to simplify the top and the bottom before I divide. 0 minus 3 is a -3. -1 minus 0 is a -1. -3 divided by -1. Negative divided by negative gives me a positive. Questions on that? Okay. Let's do a little bit of work with these then. Let us find the slope between the following pairs of points. I'll do the first one, and then I'll let you do the second one. Okay, here we're not given a graph. We're just given a couple of ordered pairs and we're told, what's the slope? I can call either point x1, y1. Let's just pick this first one, x1, y1, in which case the second point is my x2, y2. That's automatically determined. One point is 0.1, the other is 0.2. My slope formula is y2 minus y1 over x2 minus x1. Y is on top, x is on bottom. That is equal to y2, which I called negative 13, minus y1, which is 6, divided by x2, which is 0, minus x1, which is 20. Let's simplify on top. Negative 3 minus 6 is a negative 19. 0 minus 20 is a negative 20. Okay. There really isn't any simplification I could do with the numerical parts, top and bottom. But one thing I could do is note that I have a negative sign on top, negative sign on bottom. Negative divided by negative gives me a positive. So I will go ahead and write this as positive 19 over 20 as my slope. Okay. I'm going to do one more thing. What if I flip-flopped these? Let's call this x2, y2. Call this x1, y1. And I want to show this because this is a situation you might deal with. Oh, good question. You don't always divide at the end. If it is preferable that we leave our answer as a fraction or a whole number, not as a decimal. If we can simplify the fraction, say if I was able to divide the top and the bottom by the same whole number, I would have done that here. So if it were 18 over 20, I could divide the top and the bottom by 2. But here I couldn't do this. 19 over 20 is the simplest that this fraction will get. So I'm going to just leave it like that. All right. Carson, what's your question? Or Dennis?
I forgot my thing was on mute. If you left it on as
Yeah,
negative
I'm
19
ready.
over negative
Sorry.
20, would that be left at, would that be considered incorrect?
It would in this case, yes.
Okay.
Because we talked about how to simplify double negatives.
Yeah.
The fact that the slope is positive, that's actually an important feature of this.
Okay.
So we're going to get to that in a minute.
Okay.
Good question.
Thank you.
All right, Dennis, what's your question?
Sorry, I try to take my stuff on mute.
No worries.
My question would be, if the formula is y, oh, okay, I got it. So y2 minus, I thought it was supposed to go in order like hold on, what am I? Never mind, I'm confused. I think I got it.
Okay.
I was just curious why negative 13 minus 6 instead of 6 minus 13. But I got it. By looking at the formula, I think I got it.
Well, that is a good point. I mean, we don't have to leave it, we don't have to do it in this form. We could call that first point x2. Or x2, y2, and the second point x1, y1, in which case our ratio would become as follows. So it would become what? Y2 is 6 minus y1 is a negative 13. So I'm still subtracting second coordinate from first coordinate, and then there's a subtraction in my formula divided by x2, which is 20, minus x1, which is 0. So 6 minus a negative 13. We've seen this before. This becomes a single plus. So that becomes 6 plus 13. 6 plus 13 is 19. 20 minus 0 is 20. So regardless of how you choose which point you're going to call x1, y1, and x2, y2, you should get the same ratio.
Gotcha. Thank you.
You're welcome. And Max, you would have to divide the top and the bottom by the same thing. You can't divide 19 by 2 and get 12. You're generally not going to want to simplify improper fractions, no. You want to leave them in improper fraction form. Good question. Fractions, nobody likes them. But they will be helpful here. Okay? One thing that we're gonna get to in a moment is we can note that this slope is positive. So regardless of how you choose your coordinates, you should get a positive slope. Anytime you see a line with a positive slope, it will always be going up, left to right. Up, left to right. Okay. All right. Why don't you all try the next two? Try to determine the slopes of those two lines on which the ordered pairs are. I'll give you a few minutes to do that. Good. And I will note, if I agree with that, see if you can determine this one if you have not already. If I have 0 in the numerator, this actually can simplify to a whole number. 0 divided by 11 is 0, which is whole. And you can try these in your calculator just to make sure.
So what if you have 11 over 0? Would it still be considered as 11 whole number?
It would be considered undefined
Oh, okay.
number. So you'll get an error in your calculator if you try to do that.
Okay.
Just gonna go a couple minutes on this. Probably have to finish some of this up next time. That's okay. And when the denominator is 1, that's the one time that you don't have to write it. 4 over 1, 7 over 1, 3 over 1, those are all whole numbers. It's only when the denominator is not 1. Good. Just keep working. I'm gonna write some things down. Good. Yeah, I see some good things in the chat. So if you simplify above, -8 minus 20 is -28. 6 minus a -1. Double negative becomes a plus. So 6 plus 1 is 7. Okay. So that's a fraction. And we can check this to see, okay, can I divide 28 evenly by 7? I can't. 28 divided by 7 is 4, and then we've got a negative sign. So this one actually we can write without that fractional form. You might want to just kind of make yourself a note. Technically, the denominator is 1. That'll come in handy later. But if you just want to write the slope, you can write it as -4. Okay, questions on that one? Feeling okay about those? These just take some getting used to. Okay. Little note about the types of slope that we just found. So if the slope is positive, as noted above, then when we go to graph the line, it will go up, left, or right. Doesn't matter so much the number, it's just the sign of that slope. If you graph a line with a positive slope, it will always be going up, left, or right. On the other hand, if you graph a line with a negative slope, it will always be going down, left, to right. So like this last one, slope is -4. So if we were to graph it, it would go down, left, to right. Left to right. So the sign of that value actually makes quite a bit of difference. Left to right, which is why we care about simplifying it. 0 is kind of unique. If we have the number 0 is neither positive nor negative. So it's right in between the two. Therefore, if we have a line with a slope of 0, it will be neither going up, left, to right, nor will it be going down, left, to right. It will be a horizontal line. So if we happen to be given two ordered pairs and we find that their slope is 0, their graph will be a horizontal line. Questions on that? Okay. Let's do one more characteristic of lines. Do a little bit of exploration with that in the next few minutes, and then we'll call it good. Pick it up on Thursday. Slope is one good characteristic of a line that we need to be familiar with, but it's not the only one. So if all we know is the slope of a line, that will not be enough to create a graph. I could have several lines that are slanted the same, but are all on different places on the coordinate plane. Another characteristic that we want to be familiar with about lines is where they're located on the coordinate plane, not just how sloped or steep they are. And a really common value to use to determine their location is where they cross the y-axis. And we use the term y-intercept for this. The y-intercept of a graph or an equation, just depending on how that relationship between x and y is defined, is the place where the line crosses the y-axis. So for this first one, it's that The line crosses the y-axis at the ordered pair 0, 3. The y-coordinate is how we are going to determine the y-intercept. The y-coordinate of that point is 3. It's kind of hard to see. Let me zoom in a little bit. This is an xy pair. The y-coordinate is 3. So the y-intercept, we are going to state as y equals 3. Similarly, the graph on the right, I can find that ordered pair, that location where the graph crosses that vertical axis, that y-axis, telling me that the y-intercept is the y-coordinate of that point, which is 4. So the y-intercept is y equals 4. And if I know the slope and I know the y-intercept, that's actually all that I need to create the graph of an equation. But we need to be able to determine that slope and that y-intercept given a particular equation. So let's talk about that. Any questions about y-intercept and its definition before I move on? Okay. We solved several equations for y earlier. So we were given equations that had those two variables, x and y, and we showed algebraically how you could get y by itself on one side of the equation. There was an alternative reason that we were doing that. It wasn't just to make it easier for ourselves to find ordered pairs. When we were doing that, we were writing the equation in what's called slope-intercept form. And the nice thing about slope-intercept form is if you have it, the equation in this form, then you automatically know what the slope is and where that line crosses the y-axis. Slope-intercept form has the following setup. Y, so y is by itself, is equal to m, which I mentioned m. Oh, I thought it was the next lesson, but I guess it's this one. M is the slope. M times x, so it'll be a number being multiplied by x, plus b, where b is that y-coordinate of the y-intercept. So rewriting those equations earlier actually told us, well, what is the slope and what is the y-intercept of those equations? For example, let's say you're given the equation y is equal to 2/9 x minus 2. Then this number that's being multiplied by x, the coefficient of x, when my equation is written in this form with y by itself, that value will tell us the slope. We don't have to use our formula to find it. It's automatically told to us by this form. Similarly, the constant number in this form will tell us the y-intercept. Couple of others that we saw earlier. Y is equal to 3x plus 3 is one of them. Y is equal to 2x minus 8 is another. Those are written in slope-intercept form where I have y by itself on one side of the equation. This number being multiplied by x is my slope, m. This constant term, which is positive in this case, is b, my y-intercept. On the right-hand side, this number being multiplied by x, 2, is the slope, m. On the right, I am going to consider the sign before the 8 as a part of the y-intercept. So -8 in this case is my y-intercept. So it's a very helpful form. We saw these earlier. I think that I need to pause there, and then next time we'll talk about how you can use this form, use the slope and the y-intercept to put these equations on a graph. But yes, I guess that's it. Nothing else need be said at 4:45 PM. Any questions that you have? Otherwise, you are free to go. Okay, sounds good.
Yeah, you said that we could talk to you about our exam after
Mhm.
class.
Yeah, absolutely.
All right, you don't have to record this if you don't want to, but,